Okay, so in this video I'm going to look at the most recent half-term assessment on anything from the nuclear physics chapter. So we're going to start off with looking at some radioactivity. So we've got older cats often get benign tumours of the thyroid gland, but radio cat can deal with these. One injection of radioiodine is all it takes, because it gets absorbed by the thyroid and destroys the tumour. So we've got the injection happening. We're going to monitor it daily so we can check essentially when the cat becomes safe to leave. Okay, so we've got this specific isotope here, 13153, has a half-life of 8 days, and it starts off with an activity of 80 megabecquerel. So once there's a sketches graph showing how activity changes with time for the 24 days after the injection. Okay, so there's a few keys you're going to have to show with this graph. So you need to get your scaling right. So a few of these, when I marked them, I saw like people were drawing graphs up until sort of like up this sort of line here. You need to make sure you use the full axes available to you. And the key to showing this equation is you should show after 8 days, which is over here, that activity is halved, so it's 40. After 16 days, it's 20. And after 24 days, it would be 10. So that's what your graph should be showing, and that's what you can see there. I've drawn a curve of best through that data. Okay, so then looking at this specific isotope, it emits beta particles and gamma rays. Describe the composition of the nucleus. So what that means is how many of each nucleon are there. So we've got from the atomic number, which we can see on the bottom here, we know there are 53 protons, and this number on the top line, the mass number, also tells us how many nucleons there are. So 131 minus 53 tells us there are 78 neutrons, and that's where the 2 marks come from for this question. Identify 2 differences between beta particles and gamma rays. So a lot of people started talking about the different ionizing ability even, or the different penetrations, but it says it's looking for the properties of the particles themselves. So beta particles have mass and they have a charge of -1, and the gamma particles don't have mass, they're photons, and they're neutrally charged. Again, photons don't have a charge. So those are the 2 keys you'd be looking for there. You could substitute in rest energy for mass, but essentially you're going to come across the same things. Okay, so a safe level of radiation is 50 megabecquerel. Calculate how long a cat must stay in the clinic before it's allowed home. So the way activity changes time is this equation here. So A0 being your initial activity, which was 80 megabecquerel. So what we're going to need to do is first determine what the decay constant is, and we can do that using the half-life. So that's what we've got here. Decay constant is natural logarithm of 2 divided by the half-life in whatever unit you like. So I've stuck to it being in days. So I've calculated a decay constant in the reciprocal of days. Once I've done that, I rearrange this question at the top. So I've taken A0 to the side, I've taken the natural logarithm, and then divided by minus the decay constant to give the overall time, and then because the decay constant was in days to the -1, that gives us the time in days. So then last part of this question, state one assumption you've made in the calculation. Lots of people in this said stuff like that radioactivity is a random process. Well, it is. That's not an assumption, that's just a fact, so that wouldn't be relevant here. Again, people have said constant half-life. Again, that's a property of being random decay. That's not an assumption, that's just true. So the assumption you're making is there's nothing else contributing to radioactivity, or no, it hasn't been lost. So what I went for is, well, maybe the cat has excreted some of the radioactive particles. That's going to change what's going to happen. It might have some other radioactive particles. The products of the decay might also be radioactive. Any of those things could affect this and not give us the results we talked about. So those are assumptions you actually made. So assumptions should be things that are not just always true anyway. They need to be specific assumptions. Okay, so that kind of finishes the first question. Let's move on to the next one. Okay, so the equations below represent a typical fission and a typical fusion reaction. So we've got 235 uranium. It's got a neutron bound into its nucleus, causes it to decay by fission into these very typical products here, and a number of neutrons. So state the value of X and Z, so Z's over here. So let's do X first of all. So we've got 236 nucleons on this side, and we've got currently 138 and 96 here. But if we add up the proton number, we see that the proton numbers match. So charge is conserved. So what we're going to need to do is find some spare neutrons. So the initial number of neutrons minus these two will tell us how many neutrons we need left. So X is going to be 2. This one over here on the right hand side, we can see the charge on the left side is 4. Charge on the right side is currently 2. So we need 2 protons to balance this one out, and that would actually cause the nucleon numbers to balance too. So you can kind of see that either way we do this, we end up with a 2, but it's really the conservation of charge that tells us it's 2 protons there. Okay, so identify 2 similarities and 2 differences between nuclear fission and nuclear fusion. So for similarities, they both can release energy, so we can use both as fuels. So fusion is more in the sun, fission we can do here on Earth. And both types of reaction would act to increase the binding energy per nucleon. Any kind of radioactive decay does that, so that would be a similarity. So in terms of differences, fission is about splitting, whereas fusion is about combining. So that would be a key difference. Fusion requires very high temperature and pressure to cause it to happen. Fission, we don't. We just need a neutron to initiate the reaction. Another difference is we can currently use fission for fuel. Fusion we haven't got yet to work, so that would work. We use both, in terms of a similarity, we use both fusion and fission for weapons. A hydrogen bomb uses both fission and fusion, for instance. That would be a valid similarity. There's a few you could go with, but those would be the key ones I go for. Okay, so explain in terms of binding energy per nucleon why both nuclear fission and fusion reactions must produce free neutrons if they are to release energy to the surroundings. Okay, so I guess what I'm going to start off with here is actually thinking about what's going on in a nuclear reaction, because this gets people messed up, and sometimes I find myself getting a bit muddled with it as well. So let's talk through what's going on. So we've got something that's going to decay. So we've got our nucleus M. So if this is going to form something else, what I imagine happening is first we split it into lots of separate little nucleons there. So binding energy is defined as the energy you have to put in to split a nucleus up into its parts. So I'm imagining under any kind of decay, it doesn't matter, fission, fusion, whatever, we're going to split it up first, so we have to put in energy to split it up. Then what happens is we form a new nucleus there from that one, and when you form a nucleus, what binding energy tells you is you get energy out. And if this reaction here is going to produce some energy, we need to release more energy during this process here than we put in during this process to split them up. That's kind of how I think about these processes happening. Okay, so that's how we're going to achieve energy being produced. So that would be how a fuel works, but not every single kind of radioactive decay actually outputs energy. Certainly there aren't any that take in that I know of, but some are quite energy neutral. They'll be useless for fuels, but you can get decays which are energy neutral. So if you're going to achieve a higher binding energy per nucleon, which is what all nuclear reactions are trying to achieve, if you have the same total amount of binding energy before and after, what you have to do is reduce the number of nucleons in order to increase binding energy per nucleon. So that's why you need these separate neutrons to be produced as part of these reactions. Or in the cases we saw with the equation earlier, protons, it works as well. Because you can have the same total amount of binding energy going around here, but actually, because it's between fewer nucleons, this one's not in a nucleus, so it has no binding energy, that's always still going to act to increase your binding energy per nucleon there. And that's what this question is trying to get at. We are trying to achieve a higher binding energy per nucleon there. Okay, so hopefully that clears up what's going on during this process. I didn't feel that this here was clear enough or helpful enough to help you understand what's going on, so hopefully that helps. Okay, so then let's have a look at question 3. So scientists have worked out the age of the moon by dating some rocks brought back from the Apollo missions. We've got potassium decaying into argon. Both of them have a nucleon number of 40, so we'll have pretty much the same mass. We've got this process that has fixed half-life, and at the time they've now tested it, they found that we've got these amounts of argon and potassium. So we can see that most of the potassium is actually now decayed into argon. So we're going to have had at least a few half-lives passing if we've gone from 0.94, just when it was all potassium, to now 0.1. So that's halved at least twice there. Okay, so we want to use this data to get the time. So the first thing I've done is work out what the decay constant is. Like earlier, we're going to need this later on, so let's get it straight away. And what I've done in here is using the equation with number of undecayed nuclei, and the number of nuclei will be directly proportional to the mass. They'll be connected by the Avogadro's number and that kind of thing. But essentially what we can do is swap in mass for the number of undecayed nucleons there, and we end up with the same ratio there, because whatever the constant is that connects the N and M, they would cancel out. So that's what I've done. And the final mass of potassium, which is the stuff that's decaying, is 0.1. We'd have started off with 0.94 because it would all have been potassium, and argon and potassium are pretty much the same mass. We've got our decay constant, and we can calculate the half-life. We calculate the age of the moon, approximately years, or 4 billion years, which seems kind of reasonable, not too different to the formation of the Earth, so seems pretty sensible. Okay, so that completes question 3. Okay, so we're going to look at a cloud chamber. We've got a diagram from a radioactive source, and question 1 says the scale of the diagram is a few centimeters. State the type of radiation being shown. So we can see that whatever this radiation is, it's being stopped within a few centimeters because it's not continuing off the screen. What's stopped by a few centimeters there? Alpha. So really straightforward. That's obviously alpha. So we've got lots of different track lengths, but the question, it tells us it's all one type. So why might that be? Well, essentially, some of these alpha particles would have started with more kinetic energy, so they'll be able to travel a bit further before they are ionized, or if they start with lower energy, they will travel a shorter distance. So it's to do with this amount of energy they start with. Okay, so plutonium-239 is a radioactive isotope that emits alpha particles of the energies, and then the uranium itself then decays to form thorium, and they both do it through alpha decay. So write down equations to represent the decay of plutonium-239 and the decay of uranium produced. So those of you who were observant would have noticed that you were given the equation of uranium in question 2. So you know that uranium is 92,235 because it tells you we're looking at the 235. We're going to look at the 235 isotope because what's going to happen during alpha decay is it's going to go from 239 to 235. So polonium must have been 94 because 2 protons are lost. And then the same for this one, 92 goes to 90, 235 goes to 231. Again, alpha particle lost there. It was acceptable in this question to have called this 94X. this would have been x minus 2, this would have been x minus 4. I accepted that, but being a little smarter and picking these numbers up is a sensible thing to do here. Then last question, why is thorium likely to be a beta minus emitter? Well, beta minus is caused by having an excess of neutrons. So thorium, the reason it's an emitter would be it has an excess of protons. Neutrons. Okay, so let's move on to the next question. Okay, so nuclear power stations use the fission of uranium to produce thermal energy. The simplified graph below can be used to explain energy transformation by nuclear fission. Okay, so let's look at the first question. So the first question was to define binding energy. So this is the energy required to separate a nucleus into its constituent parts, or conversely, it's the energy released when a nucleus forms. So during the process of nuclear decay, like I explained earlier, I looked at from the first decaying nucleus, putting energy to split it all up, and then seeing how much energy you get out putting back together, and your reaction is going to release energy if essentially you get more energy out than you put in. That's the general idea. Okay, so then the next, use the graph to estimate binding energy of a nucleus of uranium-235. So you've got nucleon number in the x-axis, so we go up from 235 across, and I reckon that's about 7.25 there on your y-axis. That's the binding energy per nucleon, as you'll see from there. So multiply by the number of nucleons gives us the total binding energy of it. Okay, so when a uranium-235 nucleus undergoes fission, two smaller nuclei are formed, each with about half the number of nucleons. Show that the energy released in the fission of one nucleus uranium is about 4 times 10 to the minus 11 there. So first of all, this is the new nucleon number, roughly. Obviously, you can't have half a nucleon. So what we do is we go to this value on your x-axis, read across, and we find that you get a binding energy per nucleon of 8 megaelectronvolts, which makes sense because it's increased, and we know that all nuclear reactions increase binding energy per nucleon. Then we multiply that by the number of nucleons, giving us a total binding energy of 1.9 times 10 to the 9 electron volts. Okay, so now we've got the total binding energy after. To work out the total energy released, we need the difference between these two. So essentially, when we form the new nucleus, we will get this amount of energy out. To destroy the old nucleus, we have to put this amount of energy in. So the difference between those will be the energy we get released. So that's this value right here. Turn it into joules using this value, and we end up with, I got this value here because I don't think my values from my graph are particularly good, but we can see it's in the right order of magnitude for what we're looking for. I think if you'd been a bit more precise reading off your values, you'd have got something a bit closer to this value. But there we go. Okay, so that's how much energy gets released in joules. So it wants to know how much energy released by a kilogram of uranium. So if we multiply this number, the amount released per fission, by the number of nuclei that can undergo it, that would give us a total energy of 8.3 times 10 to the 13 joules, which you can see is a very large amount of energy. Nuclear fuel is very energy rich, which is one of the reasons it's such a good source of energy. Okay, so let's move on to the last question. Okay, so the process of alpha scattering was used to make early deductions about the nature of the nucleus. Describe the experiment that's carried out and how conclusions were drawn from the observations. As part of your answer, you should identify an assumption that was made and what steps were taken to make that assumption valid. Okay, so first up, by a general setup here. So we've got our alpha source, which is usually radon gas, actually. We've got some gold foil, which we're going to send the alpha particles towards. We're going to do it in a vacuum condition, because otherwise they won't even reach the gold foil. And we have some sort of detector around the outside. Sometimes you might see this as a fluorescent screen, but I'm just showing it more generally as a detector. So that's your setup. So the general setup, you get credit for 1 mark. No, it's in vacuum conditions would be a second one, because that's important. Okay, so starting from the back, we can talk about what assumptions we've made and how we can make that assumption valid. So the assumption we made is that every alpha was only scattered once, so it only interacted with one nucleus. So to make that happen, we use ductile gold foil, because that allows us to stretch it really thin, so it's only a few atoms thick, minimizing any chance of multiple scattering. So that's the assumption we're making there. So then let's link the observations to the conclusions drawn. So when you place a detector directly behind the gold foil, we notice that most alpha particles pass through undeflected. That's where we get the majority of the alpha particles detected. And what that means is most of your atom is empty space, and that all of the mass of a atom is concentrated at a very small point. That's what we conclude from that observation. The other observation we made is that some alpha particles are deflected by very large angles, and so that they've experienced actually a very large change in momentum. And if they've done that, they must have experienced a very large force, which means there must be a large density of charged particles at a certain point in the atom, which we now call the nucleus. So the small concentration of mass and charge is what we now call the nucleus, and that's how we know roughly what the structure of an atom is. And then later on, there are other experiments that come, like closest distance approach and electron diffraction experiments, to give us a better picture of what's there, but this gives us a nice initial picture to start off with. Okay, so that completes this exam paper. I hope you found that useful reviewing this exam. If you noticed any mistakes or things that are not clear, please do let me know by commenting on this video, and I'll hopefully clear those up for you.